Hello, this is Slamel here, and welcome back everyone. Today I'm going to make a video about something in maths called the Collatz Conjecture. So, first we're going to say what the Collatz Conjecture is. So, it's basically an algorithm you need to follow. So, step one is you start with any number, but not just any number. It has to be what's known as a natural number, which is basically just the numbers counting from 1, as in 1, 2, 3, 4, 5, 6, going up and up. It has to be a number like that. Stage 2 is actually a bit more complicated than that. So if it is even, if the number you pick is even, then what you do is you halve the number. And if it's odd, you don't halve it. What you do is you multiply by 3, and after you do that, you add 1. And this makes more sense when I write stage 3, which is keep repeating it. You keep repeating stage 2. How long do you do this for? Until you get 1. So I'm going to do a few examples on here to show how the Collatz thing works. Now, you might be wondering what's called a conjecture. I'll get to that eventually, but for now I'm going to follow the algorithm. So we're starting off with number 1. So you might think, now we've already got 1, we don't need to do anything, but no, we actually do need to do this. So 1's an odd number, so we multiply it by 3 to get 3 and add 1 to get 4. So that's what we start with. Then we halve 4 to get 2. Then we halve 2 to get 1. So now we've got 1. Now 2's way more easy. You just start with 2, halve it immediately to get 1. And 4 is also easy, just halve it twice. But 3 is where it starts to get interesting. And it gets more interesting from that, by the way. So 3, you multiply by 3 and add 1 to get 6. 9 add 1 is 10, so then we get 10. Now, halving 10 goes to 5, which we then multiply by 3 and add 1 to get 16. That's where I messed up there. Then we halve 16 to get 8. We halve 8 to get 4. We halve 4 to get 2. And, of course, we halve 2 to get 1. So as you can see, that's what most of it looks like. We start with a number, we go up and down a few times, and eventually we go down and get 1. Now, it gets even more like that when we eventually get to numbers like 7, which is where it starts to get long. Here's what most of them are like. So we start off with 7, we multiply by 3 to get 21 and add 1 when we get 22. Then we halve 22 to get 11. We multiply 11 by 3 and add 1, we get 34. Now, then we can halve 34 and get 17. When we get 17, we can do the same thing, multiply by 3 to get 51, and then we add 1 to get 52. Now, we can halve this one twice because it's the multiple of 4. We halve it to get 26, and we halve it again to get 13. After we get 13, we multiply it by 3 and add 1 to get 40, which is, now you can see it might get easier from here. So we halve it twice, actually 3 times, all the way down to 5, and we had 5 over here, so we just copy what we did over there, because it would apply to this situation as well. Multiply by 3 and add 1 to get 16, then halve that until we get 1. Now, there you can see it now. So, I can also do it with 9, and it will also take quite long, but I'm going to draw it here because of reasons you'll see in about a moment. So, multiply 9 by 3, get 27, and you add 1 to get 28, then you halve it to get 14, and then you immediately get 7. Now, we already know what to do for 7, so I'm just going to draw a line to here, because that's what we do next. We have to go through all of this to get all the way back to 1. So, the question is, can you do this for every number? Can you do this algorithm for every number? So a conjecture is a problem which we are trying to work out, but we haven't worked out yet. We're not sure if we can use this algorithm over here for every number or not. Now, we've tried loads of numbers, going up to really high numbers for this, and all of them have got to 1 eventually, but that doesn't mean that's going to go to 1 eventually. Just because we see a pattern doesn't mean that it's going to keep going. For example, there's this sequence here, 1, 2, 4, 8, 16. You might think the next number is 32 because there's just a doubling sequence, but the next number is not. It's actually 31. It's actually a completely different sequence here. So that's actually a sequence. I could explain later on what that is, maybe in the description or something. But that's basically, you get the idea. You can't really use patterns. So that means we might have a number that's really big that we don't know about yet that doesn't get to 1. Or maybe all numbers get to 1, but if all numbers get to 1, there has to be a way of working out that all numbers get to 1. So that's a problem which is very difficult and no one's managed to find an answer yet. But if you want to do something cool related to this, I have one thing before we finish this video. Try doing it for the number 27. Start with 27, try and get to 1. This should keep you busy for a while, just saying. Anyway, thanks for watching, and I'll see you all later. Goodbye!